We're now at the second video of this section, List of Tree Roots. In the previous video, we learned how to increment a binary number. In this video, we'll look at the element insertion, lookup, and update algorithms. We'll see how all these operations translate into equivalent binary tree operations. Time to change gears. We know that binary trees lookup and update operations are fast. Fast lookup is the result of storing actual data elements in binary trees. That is, all the roots linked up in a list. This figure will give you a better understanding. Let's write our tree definitions. Sealed abstract class tree. Define size as integer. Note the use of the sealed keyword. It's sealed, which means the definition could be used in this file only. We have an abstract method to know how many data elements exist in this tree. So, now our class tree is defined. Create the first case, class leaf, which extends tree and overrides the size as 1. Here, the leaf class actually holds the data items. As the name indicates, it's a leaf, and there are no children under a leaf. The class leaf is also defined. Similarly, we write the case for object 0, which extends tree and overrides size as 0. Here, the 0 is a singleton object. It corresponds to the binary 0. We'll see it in action pretty soon. Similarly, we create class 1 and set the size definition as t.size. The 1 class holds a tree. It corresponds to the binary 1. Just like 0, we'll soon see how it works. Now create class node, which extends tree and size as sz. A node is an internal node of the tree. It does not hold data. Instead, it holds a tree. Now let's move ahead and look into insertion. We have a helper method called link to link two trees. This helper is used by the add tree to list method, which we'll soon see. Let's define the helper function link with tree t1 and tree t2. Also, declare the node. Here's the figure which shows the linking up of two leaf trees, each having only one data element. The result is a node tree. Now let's see how we could absorb a new element into a list of trees. First, we define add trees to list function. Next, we create the case if the list is empty. Similarly, create the case 0 and case 1. And the last case to catch the error and display the error. How did it reach here? Let me explain each line. We define the add tree to list function, where the first argument, namely t1, is a new tree. Its concrete type could be either leaf or node. The second argument, namely list of trees, is a list of trees, as the name indicates. We absorb t1 into list of trees. This clause is hit when list of trees is empty, like at the very beginning of the insertion. Note its similarity with the increment method's first clause. In this case, instead of list of 1, we generate list 1 of t1. This figure will give you a better understanding. The second clause case is hit when we encounter 0. This is an empty slot, so 0 is replaced with a 1 holding the leaf tree. For example, in the previous diagram, when we add the element 13, this clause is hit. Note the similarity with the second clause of the previous increment method. Just like we replace the LSB 0 with 1 and structurally share the rest of the numbers list, we replace 0 with 1 leaf 13 and structurally share the rest of the tree list. The third clause is similar to the third clause of the increment method. For the number case, we add 1 to the LSB 1. We get 0 and a carry, which is adjusted by calling increment on the rest of the list. For the tree, when we get 1, we generate 0 and link up t1 with the tree t2 within 1. Finally, we define the wrapper method, cons, that constructs the tree. Note the argument order. We have tree list first and the new element x second. We do this so we can do a fold left method on a collection and create the tree. Let's use it. Declare the value tree equal to list, give the values in the parentheses. reversed.fold left tree list, capital B, comma, A cons. The fold left method works by taking an accumulator and a function with two arguments. Let's have a refresher on how fold left works. List of values, list equal to 1, 10. As you can see, obtain the list of the integers in the specified value. Now, write list.fold left 0, ACC, x, ACC plus x. Similarly, let's try fold left for a different value, but this time with a little modification in the previous command. The accumulator ACC needs to be the first argument. As our list of trees is the accumulator, we make it the first argument. The tree is built by inserting each element of the list successively, and the accumulator's final value is returned as the resulting tree. A great resource on folding is available at this website. You can browse this website to have additional information. Having inserted some data, let's see how to look up a random index. Note that we must land on a leaf node for the index lookup to be successful. Again, the work is divided into two methods: lookup, which locates the right tree, and search tree, which does a binary search within this tree. Now we'll write a method that performs a binary search on a tree. Define the search tree function with the arguments I and tree. Create the case clauses. The first case for 0, second and third case for any value I. Wait, I'll explain each of these cases. So, the helper searches the tree structure for the element I. There are three cases. If I is 0 and the tree is a leaf, then it means the search is successful, and we return I. Pattern matching helps us write succinct code, and clauses match when both the conditions are met. The second clause matches if I is placed on the left. It continues the search in the left subtree. Have a look at this figure. The process is very similar to how we would perform a binary search on a sorted array. This figure depicts the process. Just compare it with the tree search we have. The third clause matches when I is placed on the right subtree. The search, accordingly, continues there. Let's define the lookup method, which locates the right tree within the list so we can perform the binary search. Similarly, we write the case clauses. The case 0, ts lookup I, ts. Case 1 of ts if I is less than t dot size search tree I, t. And the third one, ts if I greater than t dot size lookup I minus t dot size, ts. Before we dive into this code, here's a diagram illustrating the scenario. This diagram depicts the various cases that crop up as the algorithm is run. Here is a case-by-case analysis. We know that B is an empty slot. The first clause checks for it and just skips it, continuing with the rest of the tree list. The second clause is hit when I is less than the size of the tree. The index is there within the tree, so we just go and search for it via a call to search, tree I, t. The third clause skips the current one. However, it needs to adjust the index. The new index is obtained by subtracting the tree size from I. Tracing out this scenario is left as an exercise for you. Now let's play with the lookup operation. Note the list reversal. Can you guess why it's needed? Writing a wrapper method to hide the reverse is left as an exercise for you. We now define the tree list and give the integer values in parentheses .reverse.fold left list tree semicolon b, comma equals cons b, comma a, now. Look up for the value at the third position in the tree. So we get the value 44. Similarly, let's try for the fourth value. Do it for the 0th position. The lookup works as expected. Awesome. Now it's time to learn about the removal method, head and tail. The removal method removes a given tree from the tree list. This works as a helper for the head and tail methods, as you'll see in a minute. By the way, the removal closely corresponds to the binary numbers decrement method. Let's define the decrement function and pass the num list as argument. list of integer. Now we write the case clauses. First one for empty list. Next, case for no decrements in XS. And third one to decrement XS. Also, we define a case where there is a non-binary number. Let's have a quick REPL session to use it. Decrement list 0, 0, 1. As you can see, the list is decremented. We decrement the binary 1, 0, 0, that is decimal 4. Binary digits are written in a reversed fashion, so the LSB would come first. This is similar to the increment method. Tracing out the execution of decrement is left as an exercise for you. The remove tree method is based on this decrement method. It removes the first one tree. And here it comes. Define the remove tree function. Pass the arguments to it. Write the case clauses. I will explain each case in detail. Here's a diagram depicting the scenario. This method returns a pair. The first element is the tree being removed, and the second is the list that remains after the removal. The first case is when we have just one tree in the list. In this case, we return the tree and an empty list. See the decrement method's first clause. The second clause is hit when we have the first tree and the rest of the list, which is non-empty. We return the tree and the remaining list. Note the similarity with the decrement method's second clause. The third clause is this, which is hit when we get a 0 element. We skip 0 and make a recursive call to remove tree with the remaining list as an argument. We must get a node in return. Why? The node's left tree is removed and returned as the first element of the pair. The second element is formed by prepending T2 to the rest of the list. Note the similarity with the third clause of the decrement method. We continue skipping 0 until we hit 1. So, here's how we've defined the remove tree. Note how we can assign names to a tuple's element. Define the value for 1 and 3 and assign the values to it. Now when you write 1, it returns the value assigned to it. Similarly, you can check for 3. We assign a tuple with 3 elements to a names list, prefixed with val. This assigns the value 1 to the variable 1 and 3 to the variable 3. The second tuple value is discarded by assigning it to underscore. You can browse this website for more examples. Spare some time to enhance your knowledge. Once we have remove tree defined, the head method is simple. Let's define the head method and pass the arguments to it. Next, declare the case. You may get the warning message, which you can ignore. As remote tree always returns a leaf node, we just extract the leaf node's data element as X and return it. Similarly, define the tail node with the arguments and write the case clause. The tail method is similar. It ignores leaf and instead returns the rest of the list. Let's give these methods a spin. Val tree list. We give the elements to the list as 11, 12 and 13, dot reverse, dot fold, left list tree b, cons b, a. Now, let's get the head of the tree list. So, it returns 11, which is absolutely correct. Similarly, let's do it for tail. Now we go for head and tail both. So, now we're done with the lookup operation. Let's move on to learn how to update a tree. How do we update an index's value? Note that we are in the immutable multi-version land. The answer is this. We return a new version of the data structure, with most of it structurally shared and copied just enough to reflect the change. Its algorithm is very similar to that of the lookup operation. We locate the right tree via setVal method and change the actual value via setVal in tree. So let's do it. Define the setVal in tree and write the first case. The clause is hit when we find the index element. In the lookup method, we return the index's value x. Here we forget the value and return a new version of the tree where leaf x is replaced by leaf of new value. Now we write the second and third case clauses. Now define setHelper function. We'll just look at one important clause in setValInTree. The rest is exactly the same as lookup. What could we say about the complexity of the various operations? For the operations on a binary tree, the worst case time complexity is big O of log n. What about finding the right binary tree? The key to understanding this is the binary number representation. The worst case time complexity is again big O of log n. In this section, we looked at an alternative list implementation, a list allowing fast random element access. We saw how all the operations such as insertion, update, lookup, head and tail perform at big O of log n. We saw how the process of structural sharing and copying just enough help with the implementation. Hopefully this has made you hungrier for more functional data structures and algorithms. So let's look at some more exciting algorithms. Stay tuned. In the next section, we'll explore about queues.